Alright, like I was saying, what stoichiometry is, it's basically the mass relationships or the mole relationship or the volume relationship. Basically, it's how all the reactants and products are somehow related to each other. Antoine Lavoisier was one of the, let me close this out here. Antoine Lavoisier was one of the first chemists to sort of recognize this idea. A lot of people recognize it. He was the first one to really put it into words and solidify the idea that mass is conserved in a chemical reaction. Now, we talked about that yesterday, and that's really important to note. All of the reactants mass is equal to all of the products mass, so long as you capture everything, right? You have to capture all the reactants and all the products, or it's not going to happen that way. And we'll see throughout the year different reactions where the mass before and the mass after is not the same, and again, that's mainly because of losing a gas or something like that. What you also have to be careful with is your balance, right? You got to use the same balance every time, but also your balance has a certain uncertainty. In other words, the mass can be within a certain range and still be considered the same value. So a lot of times students, they'll see that it's 24.39 grams the first time, then 24.41 grams the second time. They're like, oh, it changed mass. No, it didn't really, because you have an uncertainty. You have a certain amount of wiggle room within that value. So the law of conservation of mass is a pretty big idea. You know, and again, that's just an observation. Matter or mass cannot be created nor destroyed. It's always conserved. So your typical chemical equation, let me show you here. Here's your typical chemical equation. Hydrogen gas plus oxygen gas yields water vapor, we'll say. We're going to need 2 in front of there and a 2 in front of there. So what we have are the reactants, which are on the left side of the yield symbol, and then the products, which are on the right side of the yield symbol. It's very important that you recognize the reactants and products. And then we have the coefficients. Of course, we don't write ones. Anything greater than 1 we write. So these are the coefficients. And the coefficients can be, if it's gases, it can be volume. If it's, it can also be moles. It can also be molecules or atoms. Okay. We can also call it. So we not only call it the coefficient, we can also call it the stoichiometry of the reaction. That's referring to all of the coefficients. So the stoichiometry of the reaction is 2, 1 to 2, right? So the ratio of 2 to 1 to 2. So know the difference between a coefficient and just the number telling you how many atoms you have. And that's what I'm talking about here. Bless you. Balancing equations, make sure that before you do anything with any equation that it's balanced. That's where we use the coefficients. Let's try a couple. So let's do a little bit of balancing. Let's make up a one here. Let's do this. Yeah. Trying to come up with one on the fly here. Oh, let's go this. Alright, so we're going to predict the products here. So let's name these as well. I've got magnesium sulfide, then I've got silver nitrate, so those are my reactants. Now I want to be able to predict the products. So that's where I do the old switcheroo here. Magnesium is now going to go with nitrate, and silver is now going to go with sulfide. So if I just write the names on the other side, I'm going to get silver sulfide, and then magnesium nitrate. Everybody okay so far? Do I need to write bigger? I feel like my font is incredibly small. Why does this thing keep on making that noise? I'm going to close everything. What's keeping me from closing this off? Yes, close all tabs. Alright. See if that works. Alright, so let's write the formula for silver sulfide. Alright, what's the charge of silver? Take a look at the periodic table that you have there in front of you. Yeah, silver is always positive 1. So if you need to, jot it down on your periodic table there. What's the charge of sulfide? What is sulfide, first of all? Is it a polyatomic ion or a single element? Single element. What's the charge of that single element? Yeah, that's a 2- ion. So is it a cation or an anion? Anion. So what's the formula for that going to be? How many silvers, how many sulfides? 2 silvers, 1 sulfide. And that's actually going to be a solid. We'll learn that later on. Okay. Let's deal with magnesium nitrate now. What's the charge on a magnesium ion? 2+. Make sure, find magnesium on your periodic table, and so you can see why it's a 2+. And what's nitrate? Is nitrate a polyatomic ion or a single element? Polyatomic ion. So what's the formula going to be? How many magnesiums? 1. How many nitrates? 2. Now, in your notes, in yesterday's notes, turn to page 7. And I want you to jot this down. This goes on page 7 of your notes. It's where I have all the tips for you. Alright. Put group 1. NH4 plus, which is ammonium, and nitrate, are always soluble. Okay, so anytime you see a compound that has a group 1 ion, an ammonium ion, or a nitrate ion, it's always going to be soluble. In other words, it's always going to be aqueous. So if you need to jot that down, what soluble means, go ahead and do that too. So when it's dissolved in water, it's always going to be aqueous. Okay, so if knowing that information, we can figure out up here which of these two would be the insoluble compound, because nitrate that's combined with magnesium is always aqueous, so that must mean that silver sulfide has to be the solid. The reason why we know that is because if silver sulfide is not the solid, if in fact it does dissolve, then we have no reaction, right? So in this case there is a reaction. Alright, so let's go ahead and balance this reaction. Why don't you take a stab at balancing it, and then I'll go through how to balance it. It should be, it's a straightforward one. You got it? Yep. A lot of people got it. Alright, so let's take a look at it. We want to make sure we have the same numbers and types of atoms on each side. So we've got 1 magnesium here, 1 magnesium there, that looks good. 1 nitrate, 2 nitrates, so let's put a 2 in front of that. And then we have, that gives us 2 silvers, there's 2 silvers, 1 sulfur, so it's all balanced, just right the 2 in front of there. That's pretty straightforward, right? On that one. Alright, let's try another one. Let's try a combustion reaction. So this one's going to be C7H14. That's going to be a, we're going to make that a liquid, because it's kind of big, plus oxygen gas. So there's my combustion reaction. Combustion reaction is always going to give me carbon dioxide plus water. So go ahead and try to balance this one. Alright, let's try this one. So on this one, I would strongly urge you to save this oxygen until the very end, just simply because we can make that oxygen equal anything that we want it to, and then play around with the numbers. So I'm going to start with the carbon. I've got 7 carbon, so I'm going to put a 7 in front of there. I've got 14 hydrogen, so I'm going to put another 7 in front of there. So now everything except for that oxygen is balanced, right? I got 7 carbons, 14 hydrogens, 14 hydrogens, so everything else is balanced. So that leaves me, I've got 14 plus 7 oxygens, right? So that's 21 oxygens. So what do I have to put in front of this to make it equal 21? What? Nope. That'd be 22. 10.5. Right? So if I put a 10.5 in front of there. Yeah. Good. Good for you. So if I put that 10.5 in front of there, that equals 21. But I can't put a half. Like, you can't have 10.5. So that just means I need to multiply everything times 2. So if I take this and multiply by 2, it's going to be a 2 in front of there, a 21 in front of there, 14, and 14. So now it's balanced correctly. Before it was still balanced, but not necessarily correctly. All right, any questions? All right. So that's balancing. Are we okay with balancing? We can move on. Indicating the states of reactants and products is tough. And a lot of it is familiarity. There are some things that you can figure out. For instance, I said that C7H14 was probably a liquid, because the larger the compound gets, the more likely it is to be close to a solid. So hydrocarbons, small hydrocarbons, like 1, 2, 3 hydrocarbons in the chain, those are more than likely gases because they're pretty small. Anything above 3 are usually liquids because now they're pretty big, so we have these stronger intermolecular forces that we'll talk about in Chapter 11. And then, you know, up past about 9, maybe 10 carbons, now you start to be a solid. And again, it's all because of the London dispersion forces that are in the molecule. We'll figure it out as we go along. The big things for the states of reactants and products are what's aqueous and what's solid. So precipitation reactions, that's a big one. And so we'll see that as we go along. G is gaseous, L is liquid, S is solid, AQ is aqueous, which means a substance dissolved in water. Very rarely will you have a liquid, right? We don't run into a lot of liquids in chemistry, simply because a liquid is pure. And most of the things that we deal with here at the high school level are not necessarily pure liquid. So even something like methanol. So methanol, CH3OH, that is one of the alcohols that we have. Well, we don't have pure methanol. We have methanol that's been dissolved in a little bit of water. All right, so even that's aqueous. Usually the only pure liquid you guys run into are water. That's it. Because it's just water, nothing else in it. As we go along, we will remind ourselves about these chemical reactions, different types of chemical reactions. So the first type is a combination or synthesis reaction. You may remember it as a synthesis reaction. Okay. That's going to be where we take 2 or more substances, 2 or more reactants. and make one product. So here we can see a synthesis reaction between magnesium and oxygen, and then it forms magnesium oxide. And if we take a look at that, the big thing that we sort of worked on here at the beginning of the class is that the magnesium is 2+, the oxide is 2-, and that's why it forms MgO. Because you need one of each. A decomposition reaction is the exact opposite. We don't do a whole lot of predicting of synthesis or combination and decomposition reactions. A lot of it, honestly, is memorization. Carbonates will always break down to form this. Nitrates will break down to form this, stuff like that, which we don't do a lot of. Luckily, they've taken that question out of the AP chemistry exam. Like 4 years ago, there was a question that was deadly. It was always number 4, and you had to predict the products of just all sorts of different types of reactions. And so we'd spend all year literally memorizing these different types of reactions. We don't do that anymore because we don't have it, luckily. So, combustion reaction I mentioned already. Combustion reaction is always going to be a hydrocarbon plus oxygen. That's a combustion reaction. So even though this magnesium has oxygen combining with it, it's not a combustion reaction. It's a synthesis reaction. Combustion has to be a hydrocarbon. Let's try these. Sample exercise 3.3, writing balanced equation for combination and decomposition reactions. Write a balanced equation for A, the combination between lithium, metal, and fluorine gas. So let's go ahead and do that one first. So there's a combination, lithium metal. What's going to be the symbol for lithium metal? What's lithium? Li. Is it solid, liquid, gas, or aqueous? Solid. It's a metal, right? Metals are solid. Now, fluorine gas. Be careful. What's fluorine going to be? F2. Okay, very good. So, there are these magnificent 7 diatomic molecules that always appear in groups of 2. Right? It's nitrogen, oxygen, fluorine, fluorine, bromine, iodine, aspartame as well, but we usually don't include because we don't use aspartame for a lot of stuff, and then hydrogen. Okay? So again, the diatomic molecules, hydrogen, nitrogen, oxygen, fluorine, fluorine, bromine, iodine, aspartame, but we usually don't do that. So that's why it's F2, because it's by itself. So whenever it's by itself, it always forms in groups of 2. So let me jot that down here. The diatomic molecules. So this is whenever they are by themselves, not as ions, but when they are by themselves. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Alright, so what state of matter is fluorine? Solid, liquid, gas, or aqueous? Gas. So now, this is a metal combining with a non-metal. So what's it going to form? What type of compound? You have a question? Bromine, Br2. Yeah? Okay, so we got a metal combining with a non-metal, so it's forming what type of bond? Alright, it's an ionic bond. So we name these metal, non-metal ide, right? They combine according to their charges. So what is the typical charge of a lithium ion? Lithium ion is usually +1. What's the typical charge of a fluoride? Yeah, it's -1 as well. So what's the formula for lithium and fluoride getting together? Li what? F. Now that's going to form a solid. Most of your ionic compounds are going to be solids because we're assuming here that this is at room temperature. It didn't tell us the temperature. And so most ionic compounds are a solid at room temperature. I think all ionic compounds are a solid at room temperature. Is it balanced? No. So what do we got to do? Let's put a 2 here, and that balances out the fluorines. Then I need 2 in front of the lithium, and now it's balanced. Alright, let's try the next one. The decomposition reaction that occurs when solid barium carbonate is heated. It says 2 products form, a solid and a gas. Alright, so let's see if we can figure this out. First of all, what is the formula for barium carbonate? What's the... Let me bring this over here. So barium carbonate, what's the charge of a barium ion? Yeah, positive 2. 2 positive. And what is carbonate? Yeah, what's the formula? CO3, negative 2. And we are going to have polyatomic ion quizzes, so you'll be fine. They're not going to be difficult. You'll be okay. So what's the formula if barium and carbonate get together? How many bariums, how many carbonates? 1 barium. How many carbonates? 1 carbonate. It's an ionic compound, so what state of matter is it more than likely? Solid. Barium carbonate is being heated in this case, so let's draw a yield symbol. Since it's being heated, we're going to put a triangle over the yield symbol. Just as so. Now carbonates, and I don't expect you to know this, but carbonates break up into the metal oxide plus carbon dioxide. So let's write carbon dioxide first. Which carbon dioxide, do you think that's going to be a solid, liquid, gas, or aqueous? Gas, right? And then the metal oxide. So the metal oxide in this case is going to be barium oxide. We know that barium has a 2 positive charge. What's the charge on an oxide? 2 negative. So what's the formula going to be for barium oxide? BaO. What do you think the state of matter is going to be? Solid, liquid, gas, or aqueous? Solid, because it's an ionic compound. Is it balanced? Yeah, it's balanced. No. Any questions? Again, we don't do a ton of predicting the products, but there's just a couple. Let's try a combustion one. So this is methanol being burned in air. So this is going to be CH3OH. It tells you that it's a liquid, so here we have pure methanol, just methanol. Combustion, burned in air, so it combines with oxygen. And we're going to get from that always carbon dioxide and water. Go ahead and balance it if you haven't already. You got it? You good? All right.